Hello students, welcome back to the electrodynamics lectures, and today we have lecture number 3 in the series. In the previous class we have seen how to apply the Gauss divergence theorem to the expression 1 divided by r square. And why we have considered that expression is that it is part of the expression from the Coulomb's law, 1 divided by r square, and ultimately electric field being a vector quantity, so 1 divided by r square will be accompanied by a unit vector in the radial direction. So we read the vector valued function as r cap divided by r square. And for such a function, we have applied the Gauss divergence theorem. That means on the left hand side, you got the volume integral of the divergence of the vector. And on the right hand side, you have the surface integral of the normal component of the vector. And vector calculus says that the Gauss divergence theorem is always valid for vector valued function. So therefore, we expected that the answer from the left hand side should match with the right hand side. That's what we have done in the last class. And then we have ultimately arrived at two different values, 0 for the left hand side and 4 pi for the right hand side. So apparently it appears to be a paradox. Okay, so that we have not done any mistake in our calculation. If that is the situation, then how to explain this kind of a scenario is what is the discussion. So if you look at carefully what kind of function we have considered for our discussion, the function considered is r cap divided by r square. Of course, r cap is unit vector, that's okay, but what is the function is 1 divided by r square, okay, where r is the radial distance. So remember, everything is in the spherical polar coordinate and r is the radial coordinate, which means that you measure from the center of the sphere and then move outward. So 1 divided by r square function, what happens at the center of the sphere? Center of the sphere means the radius equal to 0. You have to put r equal to 0 there. So therefore, you see that 1 over r square will approach infinity at the center of the sphere. So therefore, there is a trouble in the starting point itself. That is what I mean to say. And that's the first point. And second point is that we have also taken the divergence theorem, and in which case we have to evaluate the divergence of the function. So if you see the formula, or if you see the expression for divergence of a vector in the spherical polar coordinate system, how it starts? Okay, there are three terms are there, one for each component. The first component, r component, how it looks like? It looks like 1 over r square into, we have seen that 1 by r square is the starting point. So 1 by r square into, then open the bracket, then you say that urr. Urr means the radial derivative of the r component of the u vector. So anyway, those terminologies are clear for you from the last class work. Now the point is that there is a 1 by r square term coming into picture even in the divergence. So if that is the case, what will happen at r equal to 0? So at r equal to 0, the expression for the divergence is not valid. Or we mean to say that r equal to 0 is a singular point. Singular point means it is the point for which the expression diverges to infinity. Okay, something diverges to infinity is what we can use the word exploding. At r equal to 0, something is exploding, or we say that at r equal to 0, the function is blowing up. Okay, we say that the function divergence of v blows up at the origin, which means that mathematically speaking, the number approaches infinity, and therefore, because that being the singular point, you should not use that that expression for r equal to 0. So in this particular way, if you think, at least there is a valid reason, some kind of reason is there that you should not apply the 1 over r square function at r equal to 0 itself, but a little bit away from r equal to 0 you can always use. This is equivalent, or this is easily understood when you have the expression for the electric field given by 1 by 4 pi epsilon naught. Forget about that constant. After the 1 by 4 pi epsilon naught constant, what is left out in the Coulomb's law is only q divided by r square. So when you have a q divided by r square, we are talking about r equal to 0. So therefore, whenever you have a charge located at some point, let us say r equal to 0, at r equal to 0, you have the charge q. We should not ask what is the electric field at the same point, namely the origin, because origin is already occupied by the charge. At the same point, what is the electric field? You should not ask. If you ask, mathematically speaking, it goes to infinity. That is what I am trying to explain. So the expression for the Coulomb's law itself is not applicable at r equal to 0, because that is the place where charges are present. The only question that we can ask is, away from this charge, let it be nearest to the charge, that is okay, but you should not ask the same place where it is getting occupied. So you just come little away from the charge and then you ask the question, what is the electric field? Then yes, we can always calculate. So this is the technical point that goes behind the scene that causes the difficulty that on one side of the Gauss divergence theorem you got 0 and for the other side you got 4 pi. But whatever be the case, we will have to now resort to this issue and then write down the expression, write down the mathematical expression accurately. So what can we do further in order to do this? So that is the main topic of interest. And the starting point would be to consider some kind of a function. Okay, let us see some kind of a function and see their behavior. And once based on their behavior, we can ask the question whether such kind of functions are useful for discussing the current scenario where you have a singular point at the origin. So that is the topic of today's class. Okay, so let us go back. I think I am having some graph. I want to plot some graph and show. By plotting, you can easily understand the behavior of the function at origin. Origin means just x, whatever it is. 3-dimension means x equal to 0, y equal to 0, z equal to 0. That's what you mean to say. At that particular point, we are placing the charge. Okay, let us go to the screen now. So here I am showing the first function. Let us consider at least let us consider some 2-3 functions, and I would like to plot. Let us see how it looks like. Let me bring the cursor. Is not there. I'll bring the cursor. Okay, so here now the cursor is visible. I think so, or it is too small. Wait. Yeah, here it is. So we are going to consider a function sine of mx divided by pi x. Of course, forget about this pi. These are some constants. But this m is something that we want to vary. If you don't have anything to vary, then you will get only one graph. Okay, we don't have any freedom to modify the graph. So the purpose of the m is to change the appearance of the graph by varying m. So let us start with m equal to 0 and then increase the value of m. That is the thing. And then the pi is just to scale this value. Okay, y-axis value can be changed if you put pi, or if you put 10 pi again, you can change like this. So this is not important. So the important point is that there is a function sine mx by x, and that m is the purpose of the m is that we can change or we can modify the appearance of this particular plot. So therefore, let us now plot this graph. Let me therefore plot this, and then you can see, if you observe what is happening. So as you can see that this particular graph, it is changing where I'm increasing the value for the m, and I'll show what is the value of the m for some values, for some specific value. Now I got 1 lakh, 10 to the power 5. So as m value is increasing, you can see that it is peaking slightly. And let us increase further so that whether the peaking is it is going higher and higher. And let us see what is the m value. Okay, m value is something like 3.2 10 to the power of 5. So as you increase m, what happens is I'm able to see some kind of peak coming at the origin. So therefore, let me write down this result. Okay, so what do you understand from here is what I would like to write down here. So let us consider, or let us give the name f of x, and we'll say that this is sine of mx divided by some pi of x. And then we are having a parameter. Okay, let us call this particular m being the parameter. The purpose being that you'll have to vary the structure. So our interest is that when m is taking a larger value, what happens to this particular function? So this is in terms of infinity, like m is approaching infinity. But if you want to talk about approaching 0, then we can invert it. Okay. So suppose if we invert it, then what will happen is we can write x divided by epsilon. That means m is inverted. Inverted means 1 by m. Instead of writing 1 by m, I am writing 1 by epsilon. That's all about it, in which case we say epsilon is approaching 0. So both are equivalent. Whichever is convenient, we can use it, like whether you want to say approaching infinity or approaching 0. So let me therefore highlight the version containing the m approaching infinity. So because they are equivalent. So once you have that, then we are now in a position to understand what is the usefulness of this particular function. So we will see, we will have the discussion later, but before that, let us start plotting another function. Okay, once we finish this. Okay, keep it with us. Let us have this particular function, and then let us move further to understand the behavior of another function. Okay, first function over. I'll go to second function now. As you can see that the function is again increasing or peaking, and let me show some values of m when it reaches some value, 1 lakh. Okay, so as I increase the value of m, the peak is increasing, and that means at 2 lakhs you can see that the peak is a little bit sharp, more and more sharp, right? The width is reducing. That is a point that you'll have to remember. And let us increase further and further up to 3.5 lakhs. Okay, you can see that quite peaked value is there. So let us therefore write down the similar comparison. So the nature of the function, I mean the equation of the function also, let me write down so that it is easy to compare. The equation is, let us give a different name called g of x. Okay, then g of x is equal to, we are interested in the limit of m approaching infinity. Then the function is actually m divided by root pi into e to the power of minus m square into x square. That is a function we are considering. So that is a point to be noted. Okay, so that you can compare and contrast with the previous one. And as usual, if you are interested to calculate the inverse of that, then 1 by m I can write it as 1 by epsilon, so that the limit can be written that epsilon is approaching 0. So what happens is infinity can be replaced by 0. What I mean to say is infinity can be replaced by 0 in the limit if you do that. So how the equation looks like? Now the limit, now we can write epsilon is approaching 0. Then we write 1 divided by epsilon into root pi. Epsilon into root pi. Then we have e to the power. Then we have an e to the power minus x square by, okay, epsilon square. So you see that m square is given by 1 divided by epsilon square. As usual, let me highlight the m approaching infinity version. So this is how the peaking is. So you have to remember how it looks like. Later we will discuss more about this. The point is that the height is very high. You can see something like, can you see that number? It looks like it is 2 into 10 to the power of 5. So that is the number actually. So that is a large number. When compared to what is on the x-axis, you have to compare what is the peak width here. This is 10 to the power of minus 5. So you see that 10 to the power of minus 5 is the typical width that you have. For that width, the height is 10 to the power plus 5. So this is a common feature in all of these graphs. That is what I am trying to say. If you are going to see the range between 10 to the power minus 5 from the negative x-axis to the 10 to the power 5, 10 to the minus 5 positive x-axis, then the value of the function is a large number. We are not interested in the value, but it is a large number, 10 to the power plus 5. And all these numbers are valid only for that value of m. Okay, remember that if you increase the 3.5 lakh to 7 lakhs, okay, if you increase, then all these numbers will change. Okay, it will become better. Better means the peak will become very narrow and it will be very sharp, and you get a more and more height. So this is your observation. Okay, only by plotting you can observe the behavior. So let us therefore, how do you measure this is that if you are going to increase this, we will measure what is known as the full width at half maximum. So whatever I have drawn there, that is a width. That width is a full width. Where it is measured is half of the maximum of the peak. That is why the terminology is there. So if m is approaching infinity, then what happens is the full width at half maximum is very small. It is becoming smaller and smaller. That is what you should have observed when you increase the m. Okay, I increased the value of m from 1 lakh, 2 lakh, 3 lakh, 3.5 lakhs. So every time I increase, this is what I observed. That's what I'm writing. And the same thing you can check it for the previous one also. So somewhere you find out where is the half of the height, that is half of the height if you say, then the width that you measure is known as the full width at half maximum. Okay, so the full width at half maximum, you can once again write down what is the range of x. Now you have to see for this graph what is the x, 10 to the power of minus 5. So roughly 10 to the power minus 5 is the very small value. That is what we say around origin. Remember, around origin, that word you have to be careful. 10 to the power minus 5, this side, that side means what? You are around the origin. But outside this particular region, we are not at all interested in this function. So you don't have to bother about the wavy nature. Okay, this point I would like to just to make sure what I'm trying to say here is that you follow the cursor within this small range. This is the origin. See, this is the origin. Around the origin means little bit away from this side and that side. That in this particular small region, we are interested in a function that is peaking. That has to peak to a very high value. That is important. Not a small peak. We don't want like it should peak to a maximum, whatever height possible. So in this case, this value is 10 to the power of 5. So for a small value within the origin, that kind of a small value, this is peaking to 10 to the power of plus 5. Now outside this interval, that means this side, beyond or far away from the origin, these are the points away from the origin. We are not at all interested in this function, and therefore this kind of oscillatory behavior, if it is there or not, we are not interested to take it, or we will not consider it. That's why you don't pay the attention to this kind of oscillating structure a little bit away from the origin. So we need to know the behavior of this function around the origin, because around the origin only you got, right, when you have a 1 over r square function, and when r goes to 0, that is at the center of the sphere itself, the function goes to infinity. Now because the function goes to infinity, we are searching for some function that will have its maximum possible value. And remember, you may think that 10 power 5 is not a very high. If it is so, then increase m. See, this is the graph that I am drawing for a typical value of 3.2 lakhs. If you change this 3.2 lakh to 10 lakhs, okay, if you increase this number to 10 lakh, then what happens? This peak will also go to very high value, and this width will become narrow. So full width at half maximum will become smaller. Then we say that the peak is becoming sharper and sharper. It becomes a sharp peak. Okay. So that is the idea. So why do you want this particular function is that you are now able to bring some kind of match between the trouble that we have, and then we want to address that issue. That is the reason. And we are looking for some function. It is not that you have a ready-made function for that and then you can do that thing. It's not like that. Okay, you have to search for some function which is suitable for the current scenario that we are in. Okay, so therefore this point should be clear to you, and once this is clear, I would like to show once again another graph. Okay, so this is the point. Let me write down. If m is only when m is approaching infinity, you will be having sharper and sharper peak. Okay, 3.2 lakh is not infinity, isn't it? So you have a lot of scope for making this particular peak sharper and sharper. That's the point. Okay, let me go to another. I want to go to another plot. Okay, let us give some equation number 1 and 2. So this is the first one. That where is another one? There is we plotted e to the power, right? So let us consider that as equation number 2. Okay, so what we understand from here is that at least we are now having 2 examples, isn't it? So let me therefore write down. We have equation number 1 and 2. So we are now having these 2 expressions, or they are the examples for sharply peaking functions. There are a lot of peaking function. Any Gaussian function you take, it's a peaking function, okay? But we are interested in very sharply peaking function around x equal to 0. Remember, it is as you have to put, okay? So as x is approaching 0, then the peak has to be suddenly increasing. That is called sharply. We want that kind of function. So at least 2 of them are there. Let us try one more plotting, okay? Let us consider once again one more plot, whether you have a similar behavior. I'll go to the plotting software now. Okay. So here now what happens is m is going to be a small number. So you see m is 10 to the power minus 6, smaller and smaller number. Now this is contrasting another example where m is very small, 10 to the power of minus 8. Okay, in the earlier case infinity, right? Now it is 0. So I mean approaching 0. So now I want to write down that this is another example where we are now considering something which is approaching 0. So that particular graph is now kept for here reference. Now we can write down, let us give another name, something called h of x, because f of x is over, g of x is over. I will write it as h of x as a limit of m is approaching 0 now. But there is a point to be noted. Usually whenever something is approaching 0, better to take epsilon. So I will put epsilon here, because epsilon approaching 0 is a traditional mathematical symbol. Okay, then what happens is all the m, once again, this m should be removed and put it as epsilon. So epsilon divided by pi, then you have 1 divided by x square plus epsilon square. Okay, like that you write. Let it be equation number 3. So this kind of equation, if you know, it is something like Lorentzian function. Okay, not exact Lorentz function will be there, but you will be having higher width for that. Lorentzian like function, okay, where now it is sharp peak. Similarly, Gaussian peak is there. It is not very sharp, but the peak that we considered in the last example is very sharp. So what the point is that when we are considering in our example with epsilon 10 to the power of minus 8, okay, as you can see in the graph, the nearby place, our x range you have to observe. So you just find out what is the full width at half maximum. What is the range? The range is very interesting here because it is much more smaller. You see, let me show that number here. Yeah, that number is something like that value is 10 to the power of minus 9. So you are almost near to the origin. That is what I mean to say. And exactly the x-axis value is 10 to the minus 8. Whatever is printed there. That printing may be small. That's why I'm writing. So what you see is that when you are very, very close to the origin, something like 10 to the power minus 9, only 10 power minus 9 I am away from the origin. Then what happens is it is peaking, and the peak value is something like 10 to the power 7. Okay, so it is going to a sharp peak. So this is our observation. Therefore, let me highlight once again this particular one. So we have now right now we have three examples for the sharply peaking function. Okay, so this is there, right? So we are happy with some kind of sharply peaking function. The question now is that how to use them. That is first thing. The second situation is why do we need this kind of function other than 1 by r condition. Okay, I've been telling that 1 by r condition is there, but in addition to that, there is interesting use for this kind of function. So I will also make that point so that you at least be happy to see that these kind of functions are going to be necessary for describing certain things. So let us consider a scenario. What scenario is there? For that kind of scenario, how we can use this function? So I will write down that. Okay. So consider an electron located at x equal to 0. Because we are talking about origin, right? So I will write down x equal to 0. Okay, in one dimension. Okay. So let us consider that an electron is located there. Now this is an English sentence, but I want to write this particular information in a mathematical language. So that is what I am asking, how to write this or how to express this in a mathematical language. So this is something you have to think. An electron is located at the origin is not mathematics. So you may now think about like this. Suppose if you just say that the charge q is present at x equal to 0. Okay, charge is q, right? So you are doing some mathematics. Q you are bringing. And then at the origin, what you do, x equal to 0 you can write. So if you just write q, then the information about its position is missing. Isn't it? This is what you are observing. So q alone will not serve the purpose. So q is there separately, x equal to 0 is there separately. That's what I am trying to write. Suppose if we write q at x equal to 0, do you think that we have successfully written? No. Okay, there is at here. So you give the importance for that. So that at is an English word which cannot be used for doing mathematical calculation. So therefore what happens is Q is located at x equal to 0, how will you write mathematically? So Q can be written separately, x equal to 0 can be written separately, but Q is located at x equal to 0, how will you write? That is the question. So we are in trouble now. So therefore, this is the kind of situation that you'll have to think, and therefore the functions that we have considered, right, the so-called sharply peaking functions, they will come for rescue now. So I will write that. So in this kind of situations, okay, our peaking functions, let me write down that peaking function, but remember, once again, sharply peaking, otherwise no, the other peaking functions that cannot be used. It has to peak in a very sharp way. They will be very useful now, so they will come for help. Okay, so that is the thing. Now, how to understand? Okay, let us proceed further. How do you do is that we let us not have different equations and make a lot of confusion. So let us give some kind of a common symbol for all the kind of graph that we have. We have three graphs, right? Let us give some common function for all of them because they have a common behavior. So let the symbol be, okay, let the symbol be some kind of a delta of x. Let that be the symbol. And what is the meaning of the symbol is that the behavior observed in any one of the graph. Okay, the behavior observed in any one of the graph. So the common behavior is there. Okay, so therefore one symbol is enough. So let it be delta x. I mean delta of x. So the point is that you have a peak that is happening around the origin. No, okay, near or around is better word. The peak is happening around the origin. And what about other places? Is other places we are going to fix 0 and 0 elsewhere. That means once you are coming outside the origin, we are not at all interested and let it be 0. I mean, function itself is that particular peaking function will take 0 value. So that is a common behavior that we are going to observe in any kind of functions that we have. Okay, so there is something which is not so important, but just for information, I'll write down why to consider always origin. We always say at the origin, isn't it? So that is the point I'm telling. There is nothing special about origin x equal to 0. So if you don't want origin and if you want to keep the electron somewhere else, we can write down x minus x naught. So x0 could be some other point other than origin. So that is not a problem. We can always write like this and then we can shift the graph. Okay, if you shift the graph to x0, then our job is over. So that is not a problem. So there is nothing special about the origin. Okay, you can go to any other place. But as long as the coordinate system is taking 0 there's a problem. Okay, so now we will give some name for this. Let us consider and we will give the name for this kind of an object. Object means the graph that you have seen, no? That kind of an object, the Dirac delta function. We will give this kind of a name for that. Now there is a difficulty in giving the name function. That is why I am putting it in inverted commas. It is not a real function. I mean, mathematically speaking, it is not the function like f of x equal to sin x, f of x equal to e to the power x. That kind of function properties, this Dirac delta function will not satisfy. So, strictly speaking, in a mathematical sense, Dirac delta function is a generalized function, or even better name is distribution. So let us not worry about those technical details. So our point, let us come back to our important point that the Dirac delta function can be represented by any one of the equations that we have in the previous graph. We have three of them, right? So the word represented is the place where you have to give the attention. Okay, so there are some technical points are there which has to be understood. That's why I'm writing. What is Dirac delta function? We don't have answer, but we are having some indirect answer. That's what I'm writing. Dirac delta function can be represented by any of the equations that you have in the earlier scenario, or some other suitable functions that you can discover. Three is only I am showing you only three graphs, but you can always find out some other graph, such as I will show some one or two examples. Let me therefore write down so that it will be easy for you to compare. Limit epsilon tends to 0, 1 over 2 epsilon into something like e to the power of modulus of x divided by epsilon. This is another graph. I don't want to draw the graph. you can always draw the graph and learn. Okay, so this particular function is also having similar peaking behavior. And another example is hyperbolic secant. Let me write down hyperbolic secant, the square of x divided by epsilon, then whole divided by 2 times epsilon in the limit of epsilon tending to 0. So these are two more functions that can be used instead of the 1 to 3. And not only this, you can still have more functions. So if you are having a lot of functions that can represent a similar behavior for this, then let us write down therefore the conclusion. Okay, we don't have a clear cut single function for this. Okay, so that our understanding is that equation number 1 to 5, that they are the representation for the delta function. So that means you don't have a specific function, this is delta function, like that you can't tell. Okay, like that you can't tell. You have representation for the delta function. This word representation is important. And equation number 1 to 5 is not only 1 to 5. You can also find some other function beyond 1 to 5. So there are some representation for delta function. That's fine. That's what is the fine. But if you ask the question, what is delta function or what is Dirac delta function? If you ask this question, then the trouble will come. We don't have an exact answer for that. Okay, you don't have a well-defined exact answer for that. But what is the answer is that its behavior is known. What is delta function? We do not know, but we know the behavior of the delta function. So that is how the answer is, and that particular behavior can be mathematically represented by some kind of function. So this is the answer. So how do you answer this question is that we don't have an exact answer for what is delta function, but rather mathematically represented by some kind of function. Okay, even the number of function is also a lot of functions are there. You don't have only one function. So this is the point. Let me highlight now. So what is the Dirac delta function? That is the question. The main trouble in getting the answer is that you don't have a proper answer for that. But instead of that, what you have is you can mathematically represent by. Representation is different, and this is the equation. Saying like that is different. These two things are different. And once again, you see some kind of function. Okay, that function is not also clearly defined. It could be anything. So you have this kind of arbitrariness or some kind of clarity is not there in this kind of definition. So because of this reason, so let me write down. Because of this reason, what happens is our understanding of the delta function is not very good. That is our conclusion. Okay, to how well you understood the Dirac delta function means our understanding is only weak, or we say that not a good understanding. So therefore, what we have to do is we have to, what we can do is we can investigate further. Okay, on the behavior of the delta function. You know only some behavior, right? So therefore, we have to investigate more on the behavior of the delta function. That is the one that can be done. So therefore, let me write down. If you want to understand the delta function better and better, you have to investigate more and more on the behavior of the delta function itself. That is what I am trying to say. For example, what can be done? Okay, I am not going to give any list here. At least what can be done now is that we can ask the question. At least we can ask the question: what will happen if you are going to have some function, and what is the action of the delta function on a given curve? So to understand the given curve, let us plot something. Okay, let us go back to this. Suppose if you have some kind of a data curve. Data curve means any curve that you do experiment and you get a curve, right? That kind of a curve. You plot whatever you like. And I would like to plot some kind of a graph. Maybe sinusoidal graph. I will just plot there. I'll try to put some data points. So these are the points that let us assume that collected in an experiment. Let us assume that, and we have the something like oscillating behavior. So now what I'm trying to say is that what is the connection between this and how the Dirac delta function is going to connect with this. So what are these things? Let me label that the blue color dots that you have, right? So those things we will call some kind of an experimental data points. Then let me also then show the middle region. Okay, you have a middle region, right, where there is a peak. So that also you have to now note down. That is a place where you have to focus your attention. I'll highlight that in some kind of pink color. So that region is the place where Dirac delta function is present or it is peaking. And the left side of that and right side of that, you have the Dirac delta function 0. So technically, how do you understand is that the left side region of the peaking, we say that the Dirac delta function will switch off. Switching off means 0, right? And similarly, right side of the peak, once again you say that it is switched off or turned off. But in the middle, what happens is that in the pink color region, that is the place where the Dirac delta function will pick up the point. So how many points are there? 1, 2, 3. Okay, only for 3 points, I'll put a circle. So what is interesting about those 3 points is Dirac delta function will select or it will pick up the 3 points. We will say that it will select these 3 points and the other points it will be rejected. You understand this? So there is a connection between our experimental data point or whatever data point that you have together with the delta function. So now in this way, what happened is we are now understanding about the Dirac delta function behavior. So I'll write the answer. What is the understanding that you have now is, our understanding is this. The Dirac delta function is picking up our signal. Or I mean to say selecting some of the data points. Signal means our data points. That's all about it. Where it is selecting is where there is a peaking. Okay, where there is a peaking is there. That means around the origin. Origin, I will say that x0. And at the same time, it is going to reject all other points of the signal. So there is simultaneously 2 things are happening. One is it is picking up those data points near the peaking and it is rejecting all the points away from the origin. That's all about it. So signal means some kind of data point. Okay, that's all about it. There is nothing more than that. Now here, this f of x you should not confuse with equation number 1. Because f of x, just now in the very beginning I wrote f of x. No? So don't confuse that f of x. So where it is? Here it is, that f of x. Now we are not talking about that f of x. Okay, you forgot all the graphs now. Graphs are there, that's all about it. Forget about f, g, etc. Now let us now forget about those things and give the new name. F of x means our data points. That's all. So our data points, if you draw a graph, we will call that as f of x graph. And then anyway, the delta function is given already a name, delta of x minus x naught. So I will highlight that. So once you have 2 symbols clearly, there is no confusion for the symbols. Okay, delta has a delta symbol. Our data point is f of x. So the terminology that is important is picking up some data points and rejecting the data point is very important. And this behavior, whatever we understood, has to be written down mathematically. So I will write down that. I'll go to another place of the board. And then I will try to write down how to write this. Let us see this. So what we will do now is that we have to, or let's put our observation in some kind of a mathematical equation form. In some kind of equation we have to write. Because writing the story is not the way. You have to finally write the things in appropriate mathematics. We'll write like this. We have a delta function and we have our data point. And these 2 things are there together. And what happens if you're going to consider the entire region is that if you're going to consider the entire region, that is x equal to minus infinity to x equal plus, then our interesting result is that it is going to pick up the data points. That is where f of x naught. So now you understand what is the f of x naught that you have written, that it picks up our data signal or data point around x equal to x naught. That is the meaning of f of x naught. Okay. And what do you mean by this limit is that in the entire region. It doesn't mean always you have to go to infinity. The meaning is it is an entire region, or we say everywhere. We say that it is everywhere. So this point should be clear. This meaning should be understood. Only then it will be comfortable for you. So whatever we have seen in the graph sometime back, what is the graph that you have seen? You have a delta function which is peaking. and you have a sin x kind of data points. You have some kind of oscillating, that is your data points. So you have data points together with the delta function in a same graph. That is the meaning of this product. If you always take a product and then plot, then this is what you will get. So what happens is, if you consider this, what is the meaning of this integration is, you'll have to consider this product in the entire region of interest. That's the meaning of the integration. Okay, considering the entire region, that's all about it, this particular thing. And in particular, what is the meaning is, this region should include the origin. That is a, other than origin, if you include everywhere, then there is no meaning. Okay, so what is the purpose of writing everywhere is that your region should include the origin, because origin only we are now interested, right? Either it is origin or you call it by some other name, x naught. We are interested in the trouble there. So therefore, that troubling region should be included. So that is the point. So if you include, what is the interesting thing this delta function is doing is that you have several data points, okay, in the region minus infinity to plus infinity. Several data points are there. In that, this delta function selects only, you see this, f of x become f of x naught. So what is the meaning is that x has become x naught means what? What is the meaning is that this is our data point. F of x is data point, but x equal to minus infinity to plus infinity means this f of x means set of all data points. F of x naught means it is only that data point that where the delta function is peaking. So now you understand what is the meaning of this. It picks up our signal means that only those data points or that particular region only will be selected. So this particular understanding gives you an equation like this, right? So that is the way in which you are going to define the Dirac delta function. So at least now we got some kind of a mathematical equation. First time we are getting an equation to define. Otherwise, we don't have anything to define Dirac delta function. So let me therefore write down this. Our observation I want to write down. So finally, this equation happens to be the definition. So I will make that point. We have got the definition for the Dirac delta function. So what is the definition means? Same equation. You write the integral. Okay. So that integral, whatever you wrote now, that is what I am trying to say as the definition. Okay. I will explain the term now after writing this well-behaved function, because the same expression only I am going to write down. Yeah, so let this be the definition. Now you have to understand carefully here. When you write like this, we are bringing one additional term here, where the function is supposed to be a well-behaved function. That means when I am talking about some kind of experimental data point, if you join all this data point, it looks like a sine curve, right? It could be any curve. Okay, whatever curve that you are getting in an experiment. What is the meaning of the well-behaved function is that these functions are differentiable. That's the meaning. Well-behaved mathematical function means that the function is continuous function. It is differentiable for whatever number of times you want to differentiate. That many number of time it is differentiable. That's all about it. That is the meaning of the well-behaved function. So this terminology we have to bring it for the case of the f of x, because the reason is that this delta function doesn't have this well-behaved property. This is the point to be noted. Delta function itself doesn't have the well-behaved property, because as you see the peaking function, the peak will go to infinity. If you are m approaching infinity, we have seen epsilon approaching 0, we have seen in the graph, right? So there what happens is the peak will go to infinity. So when something is going to infinity, then what happens is that its derivative will have an infinite discontinuity. So this is the trouble. You don't have this delta function is not nicely differentiable function. This is not a nicely differentiable function. So that is why delta function is not at all well-behaved function. And when you have a Dirac delta function which is not well-behaved, we can't perform any calculus operation on that. So what happens is that the behavior, that is why that behavior means the definition. That is the reason why you don't have a definition for the Dirac delta function itself. This is the point. You don't have directly the definition for delta function. But instead, how the definition is looking like? The definition is looking whenever some other function is present in the system. So this is something you have to note down. Only when a well-behaved function is joining with the Dirac delta function, then you are able to understand this integration is meaningful, and the integration really gives you some result here. So if f of x itself is not there, that means when you don't have a well-behaved function in this particular place, then the Dirac delta function itself doesn't behave properly. So that is the reason why I told you that Dirac delta function is not a real function. It is not at all a function in a strict mathematical sense. Okay, mathematicians will call this as a generalized function, or what is known as distribution. So we will not go into that particular technicality. At least you understand that performing calculus operation directly on the delta function is something which is difficult, because this particular delta function will peak to infinity. Peaking means it will spike, it will go up to infinity and then come down, and all these things will happen at a very whatever x naught, whether it is origin or whatever point. So it goes all the way to infinity and then return back to 0, near to x0. For such a kind of a function, differentiations are not possible, or you say that there is an infinite discontinuity there. So this is how the trouble is. But in spite of these troubles, we have a working definition for the Dirac delta function. So you should not say that Dirac delta function is defined as the integral of this is equal to 1. That's not the definition. Okay, that point I will explain later. Only with the delta function you should not write it as a definition. This delta function is going to be is admissible only when you have a well-behaved function. I will explain about this point later, but keep this as the starting point or the definition for the Dirac delta function. I would like to write just a point here. So what is the peaking place about the delta function is that around the x0. Okay. So the meaning of around has to be written down carefully. What do you mean by around? Means that it is little bit away, means how much little bit you have to write down. So we will write down in terms of epsilon. It is like, x has to range from x plus epsilon, little bit to the right side by a value of epsilon, and to the left side by minus epsilon. So that kind of a range should be there. And what should be epsilon means it's a small value. So you can write it something like epsilon approaching 0. It should be a small number approaching 0. Okay, we don't have exact value for that. So you have to consider whatever small number possible. In practical situations, we can consider numbers like 10 to the minus 5 is okay. 10 to the power minus 9 is generally good. So these are only practical numbers. There is nothing like, hard and fast rule saying epsilon should be that number. Anyway, 0 is far away from 10 to the power of minus 5. So that point should be 10. 0 means 10 to the power minus infinity. Okay, 10 to the power minus infinity is 0. But 10 to the power of minus 5 is okay. 10 to the power minus 9 is good. So therefore, you see that a little bit, at least practically, these kind of numbers are okay. Okay, you cannot have larger than that. So that is what I would like to say. If epsilon is something which is larger than 10 to the power of minus 5, in such cases, the definition for the delta function or the Dirac delta function, generally the definition fails. Okay, or you should not use it. So provided that we are having a highly sharp peak, only then this is fine. If you have a broad peak, okay, like a Gaussian function, it is not. So let us just go and see the graph, because already it is drawn, right? So there you can see, and then we will make a conclusion. So I think almost we have done the. So I would like to write down the conclusion for our question that we had. So in this graph, you can see the sharp peaking, and then the range of the 10 to the power minus 5, and then coming down here. Here is the question that we have asked, and now we will write down the answer for that. So what is the question that you have is, if we write q at x equal to 0, then we have a trouble because part of that is English at. So we want to write something which is completely mathematical. So how will you write? So we will now come to the answer. Let me write down in a different color. It is q times delta of x minus x naught. So now what happens is, there is no English sentence now. That's all about it. And x naught is, it could be origin, for example, or it can be any other number. So this is how you write the expression where everything is now mathematically written and nothing is in kind of in terms of some other language. So the question is clear. Our question is how to write this kind of scenario mathematically. That was the question that we asked. And now the statement that is written in this kind of yellow color is clearly an answer that we can agree upon, right? So this one, what is the meaning? Now you can even understand what is the meaning. Q multiplied by the Dirac delta function x minus x naught. What is the meaning is, Q is there, it's always a constant. Whatever it is, Q is a constant. What is the meaning of this delta function is that the delta function will have a peak at x equal to x0. So at other places, its value is 0. So therefore what happens is, you have a 0 multiplied by q, finally 0. So everywhere you will be having 0 except at x0, because x0 is the place where you are going to have a peak. And if you are going to normalize this delta function to the area 1, normalizing means what? Area under the curve. You have a peaking function, right? You just find out what is the area under the curve. If the area of the under the curve is 1, then what happens is, this fellow will become a 1 here, and therefore 1 times q will become q. So therefore this clearly indicates that if you are going to consider that this is the x-axis, for instance, this is the x-axis, and if you travel along this direction, you will be keep on saying 0, 0, 0, 0, 0, 0. Like that you will be telling. When you come to x equal to x naught, what happens is, suddenly this will say that q. How q comes? Because q into 1. So at this particular location, you say that this is q, and if you little bit go away from the peak, once again 0, 0, 0, 0, 0. So this is the set of numbers that you will get corresponding to this kind of an expression. So our conclusion is that how to write an electron is located at x equal to 0. That was the question. The answer is, we write q multiplied by the Dirac delta function x minus x naught. And of course, the Dirac delta function itself, you don't have the expression, but the Dirac delta function is defined in terms of integral along with a well-defined function. You see, now the question comes, where is the well-defined function? Q is the well-defined function. Q is a constant, right? Constant is also a function, right? When you say that x equal to 1, x equal to 1 is a function. X equal to 1 is a function because x equal to 1 is a line, straight line. So when I am saying that x equal to q, that's a constant, it is a function. It's a well-behaved function. You can perform differentiation. It is a continuous function. You can perform integration. And therefore, this particular delta function has to always take the help of a well-defined function. So this is the fundamental requirement based on the definition. So this is the very important point. And once you have this kind of Dirac delta function, and once you have this definition, some consequences are going to arise. What are the consequences? Means you can have some many properties will be, you can list out the properties by looking at the graph. For example, one of the easiest thing that can be observed right away is that it is symmetric, right? Symmetric about y-axis. If you put a peak with respect to the y-axis, left side of the peak and right side of the peak are mirror images. So we say that it's a symmetric. So Dirac delta function is a symmetric function. Like this, you can write down several properties. So those properties will be useful to address the issue. Now we have an issue. Now what is the issue? that at the center, namely the r equal to 0, center of the sphere, we have something blowing up. Blowing back means 1 by r square going to infinity. When something is going to infinity, what happens is you bring this particular delta function, because this delta function is going to peak there. So that peaking behavior, you now match with that infinity there, so that you will be in a position to now rectify the paradox that you had in the application of the Gauss divergence theorem. So that part we will see in the next class.